mechanism for dark matter. And the first one, which is, let's say, the textbook one, is the freeze out. And in the previous lecture, I began with the case of hot relic freeze out. So what do I mean by that exactly? I was working in the setup where I was focusing on the possibility, the blind possibility that neutrinos could be accounting for all the dark matter in the universe. We know, when I say neutrino, I'm talking about standard model neutrino, which are left-handed fermions. And I wanted to microphone, thank you. So I think, okay, so I was looking at the possibility to have the abundance of neutrinos that to account for all the dark matter, which is on this line, okay? And I'm just staying completely agnostic about the mass of the neutrino. So you see here that I go from electron volt to 100 TeV mass, and that we know just by looking at tritium beta decay experiment that we should be below electron volts. So I'm not realistic here. I'm just taking a case where we know that neutrinos could have been a part of the dark matter, but let's see what would have been the mass. And essentially, by looking at that, I go through the possibility of looking for dark matter as a candidate. I mean, neutrinos to be a candidate for dark matter, but more generally, SU2 left fermion to be a possible candidate for dark matter, and what should be its mass as a function of how, in which state, essentially, if it was relativistic or not at the time of chemical decoupling. So here for freeze out, until now, I'm assuming that the dark matter particle is in chemical and kinetic equilibrium in the very early universe, and is going to go first through chemical decoupling. So chemical decoupling, in this case, we usually call it freeze out. Okay, and the first case I have been considering is the possibility for dark matter to be hot relic, in the sense that I'm first assuming that the mass of the neutrino is smaller than the temperature of chemical decoupling. How do I evaluate that? In order to find out what is the temperature of chemical decoupling, I look at the rate of inelastic scatterings, in this case, the rate of neutrino annihilation into standard model fermions, for example, and I look at the moment where it is equal to the Hubble expansion rate, and I call at this moment or this temperature the chemical decoupling time or temperature. Okay, so when I'm looking at neutrinos which would have a temperature, a mass smaller than the temperature at the time of chemical decoupling, and I look at their annihilation processes, so neutrino left that could go through the exchange of Z, for example, into a pair of fermions, I essentially know from that diagram that I have two insertion of the gauge coupling, meaning that the cross-section goes at as j to the power 4, or equivalently Fermi constant to the power 2. And I'm considering temperature which are above the neutrino mass, so I have as another scale to get the right dimension for my annihilation cross-section temperature square insertion here. Also in gamma here above, I have n chi times sigma v. Okay, so in order to estimate the time of chemical decoupling, I also need to know what does the neutrino number density would look like when it's relativistic, and this we saw it goes simply as T cube. Okay, so at the end of the day, looking at what is the relic abundance of neutrino when they are still relativistic, I end up with a relic abundance that should just simply go as mass of the neutrino, and this makes this line here, okay, omega as a function of the mass is just linear, and you cross the moment where you get the right relic abundance for a mass of neutrino of a few electron volt, okay. I got a question where I think I have been a bit confusing. So if I could continue this line forever, okay, I would end up with a neutrino of whatever mass above 10 electron volt which definitively would overclose the universe. Now, once I know actually the mass, I mean, once I have a mass for my particle, or I simply look at the annihilation cross section, and I know that typically if I have gauge interactions of the type of SU2 left interaction, I should expect that essentially I have chemical decoupling around MEV scale by using just simply that sigma V goes as Fermi constant square times temperature square. I can expect that essentially here, okay, around MEV scale, I should go from particles that were relativistic at the time of decoupling, as we just considered, hot relics, to the case of particles that are non-relativistic at the time of decoupling. Okay, and so now this is exactly what I'm going to consider. Particles, okay, and in particular neutrinos that would have masses larger than the temperature of chemical decoupling for weak interactions. In that case, I essentially the mass scale relevant here to get the right dimensions for my annihilation cross section is neutrino mass to the power 2. Okay, the number density of my particle that are non-relativistic at the time of chemical decoupling are essentially going to now become Boltzmann suppressed. So it's not going as T cube, but it's exponential minus m divided by temperature times actually m times temperature to the power 3 half to have the right dimension. And here in this case, we will see that essentially dark matter relic abundance due to all these inputs essentially decreases with increasing value of the mass. And we can account for all the dark matter with the cold relic with a mass of order of a few GeV for a dark matter like neutrinos. Okay, so this is the next mechanism I'm going to consider, freeze out for cold relic. But as I said at the very beginning of the lecture, this, I mean, corresponds to this part of this possible set of dark matter production mechanism in order to go beyond just simply freeze out with the neutrino where the coupling to the standard model particles is very well known, it's gauge couplings. I'm also to be definite, I mean, for definitiveness, I'm just considering a minimal extension of the standard model where I will have a lepton coupling to a standard model gauge singlet, a fermion, Majorana fermion. And in order to write a three-body interaction, I'm going to consider an extra new scalar, which is charged under electromagnetism in order to be able to write this Lagrangian, okay? And by playing with the value of the coupling that comes into this game and going to lower and lower value of the coupling, I'm going to be able to go from the usual freeze out that I will call freeze out driven by dark matter annihilation to mediator annihilation freeze out, conversion driven freeze out, freezing, and superrim. So my goal of this second lecture is really to end up with explaining all these different mechanisms. So let me go back to the case of freeze out, okay? Freeze out, but this time with particles that are non-relativistic at the time they are decoupling, okay? And in this case, I mean, my example will be the standard model neutrino, but still let me just discuss this in a very general way, and just with first a kind of a rule of thumb estimate. Huh? So we said that in order to estimate the time at which we expect chemical decoupling to happen, we have to look at the moment where the annihilation rate is of the order of the expansion rate of the universe. And we said that the annihilation rate can be estimated as n, the number density of dark matter particles times their annihilation cross-section averaged over temperature. If I just precise also, as I said before, that we are going to focus in the case of dark matter, which is going to get produced, or I mean, let's say its abundance is going to be fixed in a radiation-dominated era. I know that I can see the Hubble expansion rate at that time as temperature squared divided by some mass scale, which is essentially m Planck. Okay, so if I use just this equality, very roughly saying that freeze out exactly happens when I have equality here, then I essentially expect my number density at the time of chemical decoupling to be just 1 over the annihilation cross-section times t squared at the time of chemical decoupling divided by m Planck. Okay. Now, what I want is not the number density of particle at the time of chemical decoupling, but I want it now, today. So for that, let's just assume that my particle is still relativistic, no reason for exciting it and to accelerate it in the whole universe in general to become relativistic again. So I have my number density today that should be equal to my number density at the time of chemical decoupling. And then I have to rescale it by the scale factors. Okay, so we know that it should go as 1 over a cube. So I have a cube chemical decoupling times a cube today here. And keeping in mind that the temperature of photons essentially goes as 1 over a. So there are some insertion of the number of relativistic degrees of freedom to be absolutely correct, but just as an order of magnitude, okay, this essentially goes as the number density at the time of chemical decoupling times t to the minus 3 at the time of chemical decoupling divided by t to the minus 3 today, okay? If I put together this and that, okay, I have that the relic abundance of dark matter today, okay, which is just the number density of dark matter times its mass, okay, it's proportional too, because I also need the rho critical, but I don't want to go through this for the moment, okay, so I have number density times mass of the dark matter. Putting everything together, I essentially see that I have mass of the dark matter divided by annihilation cross-section times v, okay, m Planck here, and I also should have some t chemical decoupling, t squared, t minus 3 in the other one, so I have essentially t here, okay? Using the dimensionless variable that we are using from the beginning of here, of these lectures in this morning, I was using x as the time variable, which is m divided by t, and let me call x freeze out, okay, the time of decoupling, so m dark matter divided by the temperature of chemical decoupling. I just have that essentially I expect my relic abundance of dark matter that to go as xf, okay, this time variable at the time of decoupling divided by the annihilation cross section times the velocity m Planck. So this is, I mean, just as a rule of thumb, this is what we expect. And actually, we are going to see that working through the Boltzmann equation that we introduced in the first part of the lecture, we are just going to recover this kind of dependency. Okay, so let me go through now the a bit more detailed analysis, just going a little bit more into Boltzmann equation. I will not go step by step. I will have to summarize a bit, but I mean, let me go a little bit less step by step, and let me study the case first, which is the simple case of the neutrino left, where essentially I have the neutrino that talk to the stamina model through gauge interaction. There is no other particles in the dark sector. And okay, let's say that things are going to be the simplest one I can have for the freeze out. I would call it the vanilla weakly interacting massive particle case. Okay, so as I said, I want to go to the Boltzmann equation, to go to more detailed calculation. And in the first part of the lecture, we have seen that essentially we can have, on the one hand, I have the Liouville operator that boils down to the total derivative of the dark matter distribution function by time. And I have to equal this to the collision term. And I am interested in the case of chemical decoupling that is set by the inelastic processes. So I'm essentially focusing on the collision term that is here below that we have introduced in the first part of the lecture. Okay, for first the total derivative.
Laura?
Yes?
Sorry, I had again problems with my microphone. Could you come back to the previous slide, please?
This one?
Yes, yes. It's a simple question. Is this all this development that you made here? It's
a very rough estimate.
Yes, but I don't see where this development is just for cold relic and instead of hot relic. What is the difference, or this is general for both?
I mean, cases? Just maybe one thing. I'm assuming from the time of chemical decoupling until now that I have something that scales as dust, which is cold. Okay, this is one point maybe. And maybe another point is that, I mean, I can use exactly the same argument and actually look at also what is exactly the expression of the number density for cold dark matter, plug this into the system, and I can also estimate the time of essentially chemical decoupling for my particle. And I will end up with an estimate that for typically weak interaction, I can, for a WIMP, so not especially a neutrino, but a WIMP in general, I can end up with this X result to be of order of 25. So you have your dark matter that is going to essentially go out of chemical equilibrium while it's non-relativistic. Yeah.
Mm-hmm. Okay.
This is essentially here that I'm playing that game. Yeah. Okay. So now I go back to the detailed calculation, and I go back to my Boltzmann equation. And I mean, with this detailed the calculation, you will see that we will end up with the same, no, not the same, more precise, but at least the same dependency. So on the one hand, I said that I had the total derivatives of the distribution function. And also previously, I said that when I can assume that my dark matter is in kinetic equilibrium, I can essentially not look at the total evolution of the distribution function, but I can just focus on the number density evolution. So I'm just going to take this equation and integrate them over the 3 momentum of the dark matter particle, okay, 2 pi cube. Okay, so here in the original form of the collision term, I have integration over the 3 momenta. So sorry, someone corrects this to me before. So the 3 momenta of over the 3 momenta of all the particles involved in the annihilation processes. The annihilation processes that I was in a very general way saying in go to thin plus dark matter. Okay, for these type of processes, assuming that I have CP invariant, so that I can consider only one transition matrix for the process in one direction or the process in the other direction. I have this collision term, and now I'm actually going to, on the top of this, add integration over the 3 momentum of the dark matter. By doing this, you can go through the math and see essentially that you have dn chi over dt plus 3h n chi here, okay? Also, to be a little bit more to the details, I'm going to consider for the collision term, I'm now going to consider scenarios where I have, let's say, 2 dark matter particles, okay, that annihilate into 2 standard model particles. Okay, so I'm going to look at 2 to 2 annihilation processes. You could consider 2 to 3 and so on. Okay, so is there a question? No. Okay, so I'm considering these kind of interaction with these momenta. Okay, and I will refer to now not the number density of chi, but the number density of particle 1 in the story, which is chi. Okay, but just for to go a little bit to be able to write more easily the rest of my equation. If you look at the system and you consider standard model particle that goes into the final state, or I mean the initial state, if you look at the reverse process, they are in kinetic and chemical equilibrium. You can actually simplify your life here in the sense that you can expect by energy conservation in the simplified frame that we are doing here, which is essentially we are neglecting the spin statistic effects. You have that F1 equilibrium, F2 equilibrium is actually equal to F3 equilibrium, F4 equilibrium. If you just take a Boltzmann distribution, I mean, you just see that this comes back. This is just due to the fact that energy is conserved. So E1 plus E2 equal E3 plus E4. Okay, this helps us a lot because here in our 2 to 2 process, F in meant depending on what I was considering here. So F in was for standard model going to dark matter. F in is P3, so F3, F4, and this was F1, F2. Okay, so I have a P4 here, sorry. And I'm just saying that the distribution function for the particles of the standard model can be considered as the equilibrium one, and I can actually just relate them directly to the equilibrium density of particle 1 and 2. Okay, so I can essentially write the full story in terms of the distributions of just 1 and 2 at equilibrium or not. This is simplifying a lot my life. Another thing here is that you might recognize partially with this quantity, and some part of the momenta, something that very much looks like the ingredient that you recover into the cross section, actually, the annihilation cross section. So actually putting all this together, you can, at the end of the day, end up with the collision term, or 1 over E, more precisely, times the collision term, integrated over d3p cube of particle 1, which is the dark matter, divided by 2 pi cube, okay, which is, at the end of the day, just simply d3p1, d3p2, divided by 2 pi cube. I don't know if you hear the dog barking outside. I'm sorry if it's annoying, but it's too hot in the room not to close the window. So at the end of the day, I can rewrite the distribution function, the collision term of my for the evolution of my dark matter particle are as the integration over the 3 momenta of particle 1 and 2, which are dark matter particles, times the annihilation cross section of particle 1, 2, times the molar velocity, okay, times F3, F4 equilibrium, which are nothing but F1, F2 equilibrium minus F1, F2. Okay, so I mean this is a much compact and simpler form of the equations. Now I want to go one step beyond, and I want to simplify even more my life. Actually, I would like to write this in terms of this famous velocity, I mean temperature average or velocity average annihilation cross section. In order to do that, I'm going to have to do a little more assumption here. What I'm going to assume is that my particle is actually still in kinetic equilibrium after it's going to it's going to decouple chemically. And I mean, the question of, does this make sense? I mean, we saw that typically for, electroweakly interacting particles, you expect that kinetic decoupling is going to happen around MEV scale, while now we are going to see, and I just mentioned it while I had a question just before, that, I mean, actually for WIMPs, you expect chemical decoupling at mass divided by 20 or so. So for a 100 GeV particle, you are above MEV. So you can essentially assume that your dark matter particle is still going to be in kinetic equilibrium while it's going to freeze out, while it's going to go through chemical decoupling, okay? And if you have kinetic equilibrium, what you can essentially do is to expect that the distribution function of your dark matter, okay, so if it's in kinetic equilibrium while it freezes out, I can expect that my dark matter abundance, or of any species that would be in this situation, okay, is going to go, I mean, I can write the ratio of F, the distribution function of my particle, okay, divided by its equilibrium density, okay, to be nothing but driven by the chemical potential of this particle, okay? So by doing this, I can essentially, I mean, you go back to your expressions of what is the number density, you can just directly understand that, I mean, because you integrate just over momenta, the distribution function, this is also the ratio of the number density of your particle at a certain time t, while it's still in kinetic equilibrium, divided by the number density at equilibrium, okay? And this is the trick that is going to help us to go one step further from here, because I'm going to be able to essentially pull out, if you want, this product of F1 equilibrium, F2 equilibrium out of this parenthesis, and somehow separate the integral over temperature from time dependence. So playing this game, what I'm going to end up with, remember that the first, I mean, the right-hand side of the equation was this, okay, dN1 dt plus 3h, where h is the Hubble rate time n1. And now I know that, so I rewrite this, dN1 over dt plus 3h n1 equal actually a certain quantity, a certain cross section, which is actually the average cross section times velocity times n1 equilibrium, n2 equilibrium minus n1, n2, okay, where sigma 1, 2, v12 is nothing but 1 over n1 equilibrium, n2 equilibrium times d3p1 over 2 pi cube d3p2 over 2 pi cube times the unaveraged sigma 1, 2 times v12, okay, f1 equilibrium, f2 equilibrium, okay? So again, I mean, going back from, this expression for the collision term, we arrive at the end of the day to this more simple form of evolution equation, not of distribution function, but of number density of, let's say, the n1, so the particle number one of this in this game, which I have assigned to dark matter. So, I mean, this is the general case where I could have n1 that is different from n2. Just to go just one step further, because I actually prefer to work with high-dimensional quantity, let me just mention that I can also express this for the comoving number density of dark matter, okay? And now I'm not using the time variable, but I'm using x, which is mass divided by temperature. I can re-express this again in terms of sigma 1, 2 times v. Now here comes a little subtlety, h bar times x, so the time y1, y2 minus y1 equilibrium, y2 equilibrium, and I should have a minus sign. Okay, so just one small subtlety here I want to mention. What is h bar here that pop-ups in this equation for the co-moving number density is that in order to go from the variable of time to the variable of temperature, I essentially have to derive, okay? I have to know what is derivative of the temperature by time. And if I know something that is conserved in the universe is actually entropy and not, it's entropy. And this helps me actually to find out what is exactly the derivative of temperature by time, which is actually minus h bar, where h bar is the Hubble rate times 1 plus 1/3 d log of hf, the number of relativistic degrees of freedom entering into the entropy, divided by the ln temperature to the power -1. Okay, so I mean, if all your freeze out is happening at very high temperature, well above electroweak phase transition and so on, I mean, typically you don't care about this. Okay, dHf over dAt is essentially constant, and you just have h there. Okay, but there's just a subtlety that will come back in freezing, so I just wanted to mention it. So now that I just have mentioned in passing this, okay, if I look at, again, I go back to this formula, I can even simplify my life if I consider, for example, that, I mean, the two particles in the initial state there are just two dark matter particles. Actually, if they are self-conjugate or not, I end up, I mean, the two particles in the initial state are two particles to a particle of the same mass and so on. So, I mean, essentially, I can relate the molar velocity to the relative velocity. I will not go into details there, but don't hesitate to ask me a question about it. At the end of the day, when I have particle 1 and particle 2, which are the same in the annihilation process, I have essentially the Rayleigh abundance, that is the set by the Boltzmann equation dn plus 3h and chi, okay, dark matter, which is equal to sigma a times v, okay, and equilibrium density of chi square minus n chi square. Okay, so this being a parenthesis, at the end of the day, this is the usual vanilla WIMP Boltzmann equation that you can find in all the textbook. Now, just to go yet another small step further, you can also usually expect that your annihilation cross-section can be written as an expansion in velocity as a term that will not depend on velocity plus a second term that will go as v squared and so on. Okay, you typically expect small velocities in the early universe. I mean, you expect actually, we are talking about particles that are non-relativistic. We are interested in cold relics. Okay, so if I go and I look at this kind of development for the annihilation cross section and I solve this equation, essentially, I will end up with omega chi h square, okay, which is 0.12, 2.2, 10 to the minus 26 centimeter cube per second for the annihilation cross section. That actually I can just write in terms of A and B just for the three first term, okay, plus dot, dot, dot. So essentially, I exchange the role of velocity with temperature. I think you also heard, this in the talk of Jesus Zavala before, the lecture of Jesus Zavala. I'm considering typically high temperatures, say J star of the order of 100, and freeze out time with XF of the order of, say, 25. Okay, so in order to account for all the dark matter in this setup, I typically need sometimes called S-wave cross-section that don't have any velocity dependence of the order of 2 times 26, 2 times 10 to the minus 26 centimeter cube per second. And this is usually where people are particularly excited when we are talking about indirect detection searches for dark matter, because this is typically what you expect to be sensitive to as cross-section. Now, just from this formula, you see that this cross-section might very well be the one that is in the early universe, but not especially the one that is today, where the velocities are much more smaller in the galaxy, for example, than the ones at the time of freeze out. Going back to my neutrino, as I very rapidly my neutrino.
I had a question in the previous slide. I did not understand that H bar thing. Like, is this the solution to this equation?
No, it's just that if you go from here, I have time dependence. Okay.
Yeah.
And I want to re-express everything here in terms of not d by dt, but d by dx. Okay.
Yeah.
So if I want to do that, at some point I will need dx by dt. Okay. And dx by dt essentially boils down to temperature by dt. Okay.
Okay.
And as soon as you want to derive temperature by time, you can. The easiest way to go is just to remember entropy is conserved. So essentially, the S times a cube over dt equals 0. And with that, you continue and you end up with the temperature over the time equal not exactly h, but h with some corrections. But as I said, usually for freeze out, somehow you don't care, because usually you consider freeze out, for vanilla WIMP, which is expected to be at energies at masses between what? 100, you can go to certain number of GeV, but typically what? 100 GeV to multi TeV. So essentially, in the case of freeze out, you don't care, but it's just to say that it should be written there. Okay.
Yeah, thank you.
So if I just
just want one clarification. Why in the expansion of sigma v, why there is not any power 1 term of v?
I should have the answer to that, but I'm going to say something that is not relevant. So I can go back to you at some point, but I prefer not to say something that is. You can find this out for annihilation cross section. There are good. Yeah. Take what the other way to go is you just take your favorite WIMP model and you try to see what will be the expansion. You will get that. But there are very good, there are simple arguments, but I don't have it here now from the top of my head. Okay, so now just one point. Just maybe one extra point here. So as I take this magic formula, I look at the case of neutrinos, okay? I plug in essentially the right cross-section for a cold relic, okay, which should be Fermi constant square times mass of neutrino square up to a certain factor. And at the end of the day, I will end up with the fact that I can get the right relic for dark matter if it's cold, it's non-relativistic at the time of decoupling with a mass of few GeV, okay, 6 GeV. Now, there is maybe another point to add up here is that for this vanilla WIMP, there is actually a limit up to which you can expect your relic abundance that essentially go as 1 over mass of the neutrino square to get this, this line, actually. I mean, if you plug into the formula I was giving to you before, sorry, you just take into account that the annihilation cross section that is here. So this is sigma A times V goes as mass of the neutrino square. You see that omega chi just goes as 1 over mass of neutrino square, and this is the reason why I have this relic abundance that just goes down as mass increases. So that just follow this. But the point is, actually, you cannot have this dependence up until the end, okay? And the reason for that is because if I really had my cross section that just is proportional to the mass of my particle, for any mass of my particle, this annihilation cross section just going to increase up until the end. And this we know it's not going to happen. I mean, the reason we know that, I mean, it's just a probability conservation, it's a unitarity limit. We know that at the end of the day, the annihilation cross section at some point should go as 1 over the mass of the neutrino to the power 2, okay? Just dimensionally, but actually it should go like this. You can go to Grist and Kamiokansky paper from 91, and you have like a development into how you get to the unitary bound. But essentially at, let's say, higher masses, you should recover at some point that your annihilation cross section goes as 1 over mass of the neutrino square, meaning that again at that point my relic abundance is going to go as 1 over sigma v, so it's going to go as mass of the neutrino to the power 2. So I am supposedly at some point going to get this behavior, this increasing behavior again, and I'm going to essentially end up with a third possibility to get the right relic abundance for my fantastic neutrino that would have whatever mass I would like to have of the order of 100 TeV. So this is the usual limit you hear about when you hear about WIMPs, is that if you look at very, very, I mean, you cannot do whatever you like. At some point, you will hit the unitarity limit. And if you take the annihilation cross section with of this form, you expect at the end of the day to have a WIMP that accounts for all the dark matter that should have a mass lower than a few hundreds of TeV. Okay, so this is everything essentially I wanted to say about this plot. And before I forget, because I wanted to do this at the beginning of my lecture, but I didn't do, so let me do it now that I have most of the participants, I guess. So maybe at some point we will have the possibility to share some whatever slides or lecture note and so on. So I have some very dirty handmade lecture notes, so not typed, but I've just put the link to these where you can get these lecture notes. And if you want some more details about the exact prefactors and so on, or if you find the typos, I would be very happy if you can tell me. Everything is in these lecture notes. Okay, so this was for, let's say, the vanilla WIMP, or let's say the case of the zero level dark matter candidate you can think of, which is the neutrino of the standard model, the neutrino left. And essentially, we have seen that we could account for all the dark matter with this guy for making use of freeze out. Would it be with a hot relic, with a cold relic? But at the end of the day, we know it doesn't work, because all the possibilities we have is to have a mass of neutrino which is much higher than what particle physics experiment or even cosmology tell us that it makes sense to look at. Okay, so we definitively have to go beyond the standard model. And this is where now I'm going to the case of this leptophilic scenario, and where I'm going to begin to look at some more, let's say, maybe complicated, intricate version of freeze out. Okay, so I now want to look at freeze out due to co-annihilation. Okay, so in the case of co-annihilations, what do I need is essentially that I have, so assuming that I'm still in the same framework as before, I have dark matter. I have a set2 symmetry that prevents my dark matter to go to decay directly to the standard model. And let's assume that actually dark matter is not alone, but that I have dark matter partners that could be Z2 odd. And actually, when these particles have masses which are similar to the one of my dark matter, I should definitively take into account that they are there and that they interact with the standard model in order to compute correctly my relic abundance for dark matter. Actually, the processes I'm going to have to take into account, assuming that I have, let's say, a certain number of particles that are Z2 odd that I will call chi I for a few minutes. Okay, I could have n particles which are Z2 odd. Okay, in order to compute the relic abundance of dark matter, I should definitively take into account not only annihilation cross section of two Z2 odd particles, let's say I and J. Okay, so chi ij, by chi ij, I will refer to annihilation cross section of chi I, chi j, going to standard model, okay? And chi I and chi j are annihilating and are not especially equal. Chi 1 going to standard model is the case before, okay? I also have to take into account conversion, what I'm going to call conversion processes. So I will have chi I, refer to sigma I going to sigma j as all the processes where I have one particle of the dark sector that hits some standard model particle and goes to another particle or the same particle of the dark sector and another or the same standard model particle. So these are conversion scattering processes, or okay, so sometimes called co-scattering processes. And I will also have to take into account decays or inverse decays, depending of your point of view, of chi I going to chi j and standard model particles. Okay, so on very general grounds, without being more willing to be more specific, if I take into account all these processes, I was saying before that I had an ugly Boltzmann equation when I was not considering the two particles, especially to be, taking N1, N2 and going to 2, 2, 2, 2, and so on. Actually now I'm going to make things even worse. I'm just going to copy some part of my lecture notes in order to hopefully not put any more typos, okay, in the copy paste. Okay, at the end of the day, when I'm considering the case of the possibility to have co-annihilations, I actually have to solve a set of E equal 1 to n, okay, so n Boltzmann equation, okay, of the form as what I just copied below. So you see on the first line, I have the Liouville operator for each species. On the right-hand side of the equality, I have the first term, which you recognize from before, so just annihilation cross-section times molar velocity times the product of number density minus number density at equilibrium, but I also have to take into account conversion processes and decays and inverse decays. Okay, so on very general grounds, I would have to do all these theory. Okay, let me go one step further. Okay, and just because I will use it later, I'm just going to flash you how this horrible equation can look a bit more compact when you go to let's say a more using these quantities which are adimensional. First of all, in order to go one step beyond, I would like to emphasize that you can actually use not annihilation, cross-section, or decay rates, but in general, and this comes from people which have been playing with leptogenesis and so on, you can introduce conversion, reaction rates, which, in, let's say, one single notation, essentially, if you consider just 2-to-2 processes or 1-to-2 process annihilations or decay, you have these gammas, which essentially corresponds to either annihilation, cross-section, or conversion processes of the type of decays that you can consider here. Okay, IJ, KL are not especially, so here it's a bit confusing because IJ, KL is not especially for particles of the dark sector, but for any particles. So I and J could be, I could be dark matter, J could be standard model, or J could be dark. But just to say that there is a way using these reaction rates, you can actually rewrite the equation I had before in this form, okay, where I should have actually H bar here, okay, for the co-moving number density. And here suddenly, somehow I have compactified all annihilation and co-scattering processes into this gamma, okay, and all decay and inverse decay processes into, yes, it's also a gamma, and into that gamma, okay? So just to tell you again, sometimes it's useful to go from dimension-full quantities to dimensionless quantities, and it can even become somehow more easy to handle or to discuss. Okay, but that was again a side note because I want to first discuss the case. It will be relevant when I will begin to discuss co-scattering freeze-out, which will be the very last topic I will discuss today. But before going that, let me go to the, let's say, vanilla co-annihilation case, okay? And in order to go to the vanilla co-annihilation case, I'm going to make a certain number of observation, which is that actually what we expect, what is going to happen? We have a bunch of particles, okay, in the dark sector. But at the end of the day, all these particles, as soon as they are going to freeze out, they are going to decay to lower mass particle of the dark sector. Up to the moment you end up to the last, to the lightest particle of the dark sector, which is going to be your dark matter, okay? So one thing that is interesting to do is to just simply look at N as the sum over all the particle of the dark sector number densities, okay? And essentially you can look at that, and you can look at the end of the day the Boltzmann equations for this total number density, and you end up taking into account all the previous equation with just simply having to take into account any co-annihilation processes. You can even go one step further again and assume the same thing as before. Actually, I'm going to assume that all the particles, all these dark sector particles are in thermal and chemical equilibrium in the early universe, okay? And I'm essentially assuming that all conversion processes are happening fast enough, okay? So all processes, chi A, chi J, okay, are happening fast enough. Would it be co-scattering or decay and inverse decay processes, so that I can actually just simply say that in general, I expect the chemical potential of particle Y to be the same as the chemical potential of particle J, Okay, so essentially, going back to what I was using before, I can expect that the number density over number density at equilibrium is equal to e to the minus mu I divided by temperature. And this is because we are expecting to have originally fast conversion processes, even around chemical decoupling, where annihilation process go out of equilibrium. If these conversion processes are fast enough around that time, I can assume that mu I, the chemical potential of species I, is equal to chemical potential of species G, and actually that this is equal to Nj over Nj equilibrium. And even going one step further, that at the end of the day, for any species, I can relate the ratio of the total number density divided by the number density, the total number density at equilibrium, to the number density of one species. So this is going to allow me to go one step further and to simplify my life and to recover the total number density on the two sides of this equation. Okay, so working with this assumption, okay, I end up again with a very simple and nice expression for the total number density that at the end of the day will be the one of dark matter, because all heavier particles are going to decay into the dark matter fast after freeze out, as a certain annihilation cross section, a certain effective annihilation cross section times n square minus n equilibrium square. So you recover Boltzmann equation. So by dot, I just mean dn by dt. I'm sorry, I didn't use it before. So let's continue with the same notation. dn over dt plus 3hn equal minus sigma v effective, some kind of effective annihilation cross section, times the number density square minus the total number density square at equilibrium. And essentially, okay, sigma vf is the sum of all these annihilation and co-annihilation processes times velocity averaged over the temperature times the ratio of n equilibrium of a given species over the total n number density of the dark sector. Let's call it like that. Okay. So just to be a bit more, let's say, clear or precise, or more illustrative about what I mean by this effective annihilation cross-section, I just want to illustrate the case of co-annihilation in this beyond the standard model scenario I mentioned before. So if I go to the case of the leptophilic dark matter, where I have my Lagrangian that includes an interaction term between some singlet Majorana fermion, okay, singlet over standard model gauge group that couples to a right-handed lepton and a scalar field, which is charged under electromagnetism in order to have a Lagrangian that is invariant under all the standard model gauge group, plus Hermitian conjugate. What do I have as processes that can enter into the game? First of all, I have the possibility to have dark matter annihilations. So for example, chi-chi going to leptons through the exchange of a scalar particle, okay? In this case, I have two insertion of my lambda chi coupling of my Lagrangian, okay? Two insertion of my Yukawa coupling. So if I want to describe dark matter annihilation, that I would call sigma 1,1, it's annihilation of 1 with 1, okay? I expect this to go as lambda chi to the power 4, okay? Amplitude goes as lambda chi to the square, so annihilation goes as lambda chi to the 4th, okay? Then, I mean, I could also have, if phi and chi are near in mass, I could also have the relic abundance that is set by co-annihilation processes. So where I would have a phi, a scalar, okay, and a dark matter that will co-annihilate. So if I use the usual notations, scalar, fermions, they are going to through this lambda chi coupling I have again, okay, go to a standard model lepton, okay, and for example emit a photon or a Z boson and have another lepton here of the standard model, okay, so I would have photon on Z boson. In this case, okay, I have a lambda chi coupling here, I have a gauge coupling there, so I expect my co-annihilation, okay, cross-section to actually be proportional to lambda chi square gauge coupling square, okay? And finally, the other processes that would come into the game is actually the scalar annihilation with itself, the mediator annihilation, okay? So I could very well have the scalar that is charged that just annihilate directly through a gauge coupling square insertion into two gauge bosons, for example, and I have my sigma to 2, my annihilation of the mediator with itself, of my second particle of the dark sector, proportional to j to the power 4. At the end of the day, I expect my relic abundance if I have not a very big mass splitting between the masses of my scalar and my fermion to scale at the end of the day as 1 over sigma v effective, okay? And the sigma v effective is expected to go as 1 over sigma 11 v, okay? If I have my relic abundance that is driven by mediator annihilation. Now, if I have, by dark matter annihilation. Dark matter annihilation freeze out, I will call it. Now, if for some reason I have not such a big lambda chi coupling, okay, actually not so big compared to the gauge coupling, maybe actually these processes are going to enter into the game and are going to be relevant, okay? And the way we know it's going to become relevant is actually, my annihilation cross-section itself essentially will scale at 1 over sigma v 1, 2, okay? But in this sigma v effective, I had some, number density at equilibrium of the species that were entering into the game. And remember that, particles which are non-relativistic have a Boltzmann suppression. And if my particle, my friend, my partner, my mediator is a little higher in mass than the dark matter, it could be, you need nothing. It could be, its density could be much more suppressed than the one of dark matter at a given time. So if you have a large mass splitting, so you have to be careful. So you have to keep in mind that you actually have exponential minus delta x, where delta is m1 minus, m2 minus m1 divided by m2, and x is just the freeze out time variable, okay? So you have to be careful that this delta is not too big. If not, this co-annihilation term is not going to play any role. But if delta is not too big, okay, and actually my gauge coupling is actually much higher than the lambda chi coupling here, actually co-annihilation can play a role, and I will be in co-annihilation freeze out. Now, again, I can go to the case where actually lambda chi would be very suppressed, okay, and my mediator is annihilating through a gauge interaction, which are very unknown, which are fixed, J is fixed. So I actually, if again, the mass splitting between the partner and the dark matter is not too big, I could very well have my effective annihilation that is completely driven by this term, and that I will call mediator annihilation freeze out, okay? So what I'm just telling you, you can see it in this graph, I mentioned I showed, I flashed at the beginning. Sorry?
That's what I thought.
Someone has a microphone open. Okay, you still hear me? Okay, looks like. So essentially, lambda chi to the power 4 here. Okay, so essentially what I have just explained you is this part of the graph here. So I have relic abundance of my dark matter on the y-axis, and on the x-axis I have the coupling. Okay, and what I just told you is if I have a coupling of the dark matter with the standard model through this mediator that comes into the game. Okay, I will have my relic abundance that my coupling is of the order of the gauge SU2 coupling or a bit larger. I expect my relic abundance to be set by dark matter annihilation. Okay, annihilation cross section goes as lambda chi to the 4, meaning that the relic abundance goes as 1 over lambda chi to the 4. This is, let's say, the vanilla WIMP scenario, and this is how my line should be in this region where couplings are of the order or a little bit larger than SU2 gauge coupling. Okay, this is, let's say, the standard WIMP. Now, this is not the end of the story. Even if I have a coupling smaller than what I would expect for a vanilla weakly interacting massive particle, I can still get the right relic abundance, but through co-annihilation. So through these sort of processes, where I have dark matter that annihilates with a partner, okay, or just actually the partner annihilation, the mediator annihilation that is just going to drive the value of the effective annihilation cross-section. And if the mass splitting between the dark matter and its colleague in the dark sector is not too large, actually, I could very well have my relic abundance completely set by essentially the gauge coupling and be absolutely independent of the value of lambda chi in order to get the relic abundance. And so this is another example where actually you cannot directly relate these 2.10 to the minus 26 centimeter cube per second between, that relates to the value of the effective annihilation cross-section, which has nothing to do in the case of mediator annihilation with the dark matter annihilation. And you cannot relate this value of the cross-section to the cross-section that is relevant for indirect detection searches. So, I find it interesting. I just want to mention in passing that in this scenario related to indirect detection searches and gamma ray searches, that you should not always just focus on, let's say, 2-to-2 annihilation processes, but you should potentially also check that actually three-body annihilation and loop annihilation through a loop can actually be relevant, again, when there is a small mass splitting, when by three-body annihilation, I essentially want to mention that, you could have virtual internal Bremsstrahlung emission, okay? These can give rise to a line-like emission, and actually, okay, it can be relevant for Majorana fermion that I'm considering as my, let's say, toy model here. It's extremely relevant in the case of a real scalar, okay? This is something that can really drive the signature of dark matter for indirect detection searches when it's a lepton. If your fermion defined as state is a quark, you can actually even have strong contribution of this three-body interaction in order to set the relic abundance. And so in the link to the notes I give you, you can also check, there has been some literature on that at some point when people were excited about all these things. And maybe just before I stop on this co-annihilation story, I just want to flash, because I had a question in the first part of the lectures of, is my particle, can I consider that I have kinetic equilibrium when I'm considering mediator annihilation freeze out? And the answer is, I mean, you should check, okay? But this is just an example, okay, where I have, okay, a slightly different value of the mass of the dark matter, okay? And I have a coupling 10 to the minus 3 here. And actually, you can see that essentially you have the conversion processes, which are those ones, okay, that convert chi into the scalar, into the partner, which are represented by the continuous red line and dashed red line. And here you have essentially the interaction rate divided by the expansion rate of the universe. And what you see is that, I mean, for this scenario, at least for when I'm considering a coupling of 10 to the minus 3, okay, I essentially have conversion processes that are fast enough in order to be allowed to use all these tricks I have been using here, where I have chemical and actually kinetic equilibrium between the dark matter and the partner. So maybe I just do a very short 1 minute break for me to be able to drink something, and I come back to you. And if you have questions, please just go ahead on this part.
Laura?
Yes.
I have a question with respect to the production mechanism. Could you go to this to the Feynman diagrams? Please.
Which ones? These ones?
Yes, this part. What about what is called forbidden dark matter? Can you have, for instance, instead in the first diagram, instead of the leptons in the final state, to have the mediator, which okay, it's a bit higher in mass, but I
yes,
have
I mean
seen
you're asking me if I could have is it really called forbidden dark matter or secluded dark matter more? You are talking about secluded dark matter, right? Where you have annihilation
actually,
of the...
No, for I was thinking in forbidden. And in my understanding, it works. That process should work.
But yeah, okay.
Provided
The point, I mean,
mediators...
this process exists, but I mean, right now I'm assuming, and I maybe didn't say that very clearly, I'm assuming that chi or chi1 is the lightest particle of the dark sector, so it's lighter than phi,
yes.
than the mediator. And what you were saying is that if essentially this was the only possible process for my dark matter, I would essentially have not the possibility for dark matter to annihilate, okay? But the point is that this is not, I mean, annihilating, maybe I should put a bubble here. If, I mean, I was in the situation where my mediator was maybe slightly higher in mass than the dark matter, and for some reason, this was the only process I have, maybe I can just annihilate into the scalar for certain a certain mass where I have just enough kinetic energy to get there, right? I mean, this is your point, right?
Yeah, exactly.
But the point is that I have the possibility to go to leptons, and they are much lighter in mass, and I have no reason not to consider these diagrams. So I cannot play the game of, like, I mean, forbidden dark matter or secluded dark matter, let's say in the framework that I have set here. But this could be, indeed, forbidden dark matter would be a possibility that I'm not going to go through today. But yes,
no, it's okay.
This is another possibility. Yes, I agree.
Mm-hmm.
Okay, but not, let's say not relevant for the setup I have chosen as an example to go through a maximum number of possibilities. Okay, so I have still a bunch of scenarios of mechanism to go through, and I have already the feeling that it's going to be a bit short, but let me try to do my best. So until now, I have considered, let's say, probably something that I could call textbook dark matter freeze out annihilation and so on. What I want to look at is now the possibility to have feebly interacting massive particles, okay? And I mean, maybe you can ask the question of what is really feebly interacting massive particle. By feebly, I mean much less coupled to the standard model than weakly interacting massive particle. To be very sincere, I think here, I mean, I could just say that, I mean, a particle with couplings of the order of 10 to the minus 2 or so is a weakly interacting massive particle. But a particle that has coupling much smaller, so even in the case of mediator annihilation, I'm not sure how I have to call this particle, okay? For me, it's not really a win, but okay, let's say that mediator annihilation freeze out and relic abundance set by dark matter annihilation would be, let's say, WIMP example. And now I want to go to the cases that I have here, okay, to the production mechanisms that are super WIMP, freeze in, and conversion driven freeze out. And let me begin with the, let's say, most well-known one by now. I mean, maybe you prefer, I would have preferred to that I begin by another one, but let me begin with freeze in, okay, which is usually the mechanism that you, when I say FIMP, I think the first thing you have in your mind is a FIMP is something which its abundance is set by freezing. And okay, so this is the nomenclature that has been used in the literature, certainly. But let's say that here I will use FIMP for something that is very feebly interacting with the standard model. So I'm working in the same setup. I have a Z2 symmetry that helps me to differentiate the dark sector from the visible sector, or let's say the standard model sector. And I'm assuming that my production is going to happen in a radiation dominated era. So let me consider freezing first. And as in the case of vanilla, weakly interacting massive particle, let me just give you a rule of thumb here for its abundance. So what I'm going to assume now is my particle is so feebly coupled to everything that it's not in chemical equilibrium and that is not in kinetic equilibrium in the early universe, okay? So I'm going to produce my dark matter from scratch, okay? And in order to produce it from scratch, okay, this is going to depend on the setup I'm considering, but here I'm still considering the case where I have a bath particle and a dark matter that talk to each other through this, say, three-body interaction. What I'm going to do is to slowly produce my dark matter from the beginning of time, let's say after inflation, until today. I'm going to assume here, and I know we could enter into discussion, but I'm going to assume that initially I have zero number density for the dark matter, and that I'm going to produce it from, let's say, for example, the decay of my bath particle. Okay, remember I had bath particle that decay to some standard model particle and the dark matter. So this is the case of the leptophilic scenario. Bath particle is my charge scalar and my standard model particle is a lepton. But at the beginning of the first lecture, I was just giving you a set of example where you could recover exactly the same kind of three-body interaction, which will a bit depend on what you assume for the standard model particle and what you assume for the spin of the bath particle or the dark matter particle, for example. Okay. So how can I evaluate approximately the amount of dark matter I'm going to get from freeze-in? Okay, I'm going to get the typical abundance I expect to get from the rate of production of my dark matter times the time that has been passing since the beginning of the moment where I'm considering my production. So considering like the usual inflation that happened some time ago, and that we have a radiation dominated era, the typical time that has been evolved is Hubble time. Okay, so it's 1/h at a given temperature, which is M Planck essentially, okay, divided by temperature square. And the rate of production of my dark matter, I can essentially estimate it as the decay rate of my bath particle in rest frame, okay, into Ka, let's say, divided by the Lorentz factor due to, time dilation, yes. So essentially, gamma is of the order of the energy of the bath particle divided by the mass of the bath particle, which is essentially temperature over mass, okay? So essentially, I expect my relic abundance of dark matter from like production from the decay of some bath particle into dark matter to go as the decay rate, okay, times mb over t times m Planck over t squared. Okay, so essentially this goes as 1 over t cubed. So what you see here is that the lower is the temperature, somehow, I mean, that the dark matter production is more efficient, okay, in this scenario. So this is sometimes why you hear that freezing is an infrared process, infrared dominated process. Now, if I re-express this in terms of a dimensionless variables, that from no one, okay, I'm still using x is some mass scale divided by temperature, but now the mass scale is going to be the mass scale of my bath particle. Okay, so let me be very let me insist on it. Okay, if I take this definition of my time variable now, I expect this to go as b chi m Planck x cube over mass of the bath particle square, and keeping in mind that I expect this production of dark matter to be the most efficient at the lowest relevant temperature, I can think that actually what is the most relevant lowest temperature in the case of a bath particle decaying to a dark matter particle in a standard model. I know that the abundance of my bath particle is going to be, I mean, the abundance, it's co-moving abundance is going to be fixed up to the point this particle is just going to become Boltzmann suppressed. So when there are no particles around, I'm not producing effects efficiently anymore, dark matter. So essentially, I can expect that I'm going to have the right, I mean, I'm going to guess the abundance of dark matter essentially at the point where my bath particle becomes non-relativistic. So where x equal mb over temperature is of the order of 1, okay? So putting all this together, I essentially expect my relic abundance of dark matter to scale like bath particle decay, okay, times m Planck divided by mass of the bath particle square, okay? This is a rule of thumb, and as in the case of freeze out, actually, we are going to recover this kind of dependency going through the details of the Boltzmann equation. So let me go back to the Boltzmann equation. If I didn't mess up too much my first slide, okay, let me take this Boltzmann equation and copy it now. Okay, so these were the so I could have copied it. I'm sorry. I mean, this was not very relevant, but it was just to say essentially that I'm just copying the same again and again. So times the amplitude square. Okay. Now I'm assuming that I have a very, I mean, I don't have dark matter initially. Okay. So everything I'm interested in is the process of production. So if I go back to my notations before, production of dark matter, so from some initial state plus some final state plus dark matter, initial state leaving the bath particle to the standard model plus dark matter, times the initial state number density particle times some spin statistic. And so as I said in the first lecture, in the case of freezing, the spin statistic factors can have a role actually, but I'm just going to neglect them and not discuss them into the details. And I send you back to a discussion that you can find in the microbegas paper for more details. So let me focus on this collision term for dark matter production for freezing, assuming that there is no dark matter initially. Again, I integrate this over the 3 momentum of the dark matter, and you can actually essentially end up with the evolution of the number density of the dark matter particle to be directly, I mean, the initial particle state is the bath particle, to be essentially driven by number density of the bath particle times gamma B to chi, the decay rate times some modified Bessel function of the second kind. So this is a fantastic name, but it's essentially the temperature averaged Lorentz boost factor, essentially. But I mean, if you go, you just integrate out your equation, you will just end up with this exact expression here. Okay, so going back to the fun of, I mean, again, you can go back to dimensionless variable, and we write this in terms of dy chi over dx gamma b to chi in the case where just decays are the most important, x h bar, yb, equilibrium k1 x over k2x. So these are essentially these are the equations for my abundance comoving number density of dark matter. And if I plug I just integrated out, I would just flash you the results, but essentially you have, I'm just going, so maybe I copy it, or I just show it to you. So I just have exactly the form I was expecting for my rule of thumb estimate, which is that my comoving number density of dark matter is just some fantastic prefactors of 400 square root of 5 divided by 4, blah, 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 whatever, okay, times the number of degrees of freedom of my bath particle divided by the number of relativistic degrees of freedom that enters into the entropy density times the number of relativistic degrees of freedom entering into the radiation energy density to the power 1/2 times these factors that we guessed from the rule of thumb estimate. Okay, so this is very nice. We are happy. We understand where things comes. And if I plug numbers into it, so if I take the entropy density, today I multiply, the dark matter density at the time of freezing. So essentially the time where the production from the bath particle just falls extremely rapidly down due to Boltzmann suppressed bath particle number density. Okay, I end up with a relic abundance of the dark matter that should be of the order of 0.12, okay, times the mass of the dark matter. So the mass of the dark matter just comes from the fact that I want the relic abundance today. I'm assuming that my particle is non-relativistic today. So I have mass times number density, and this is why I have 1 extra power of mass of dark matter in my relic abundance. I have the mass of my dark matter divided by 2 power of the bath particle times the decay width of the bath particle. And if you plug some numbers into it, I want to get 0.12 for the relic abundance of dark matter. I see that for a 10 keV dark matter mass and a 1 TeV bath particle, I need essentially a decay rate times the number of degrees of freedom of the bath particle to be of the order of 10 to the minus 15 GeV. And actually, if I again estimate, let's say that the mass of my bath particle is the largest one in the story, much larger than the mass of the dark matter and the mass of the final states standard model particle, could be lepton, for example, I expect to have a decay rate of the order lambda chi squared divided by 8 pi than the mass of the bath particle. And again, if I take a 1 TeV dark matter, I essentially expect my coupling in order to get the right relic abundance through freezing from decay to be of the order of 10 to the minus 9, 10 to the minus 8. So a coupling much, much smaller than the gauge coupling of SU2. Okay, and so this is why you really make the distinction between feebly interacting massive particle, feebly being much, much more feebly interacting than weakly interacting particles. And so just to also show you the the case, I mean, more precisely in the setup of leptophilic dark matter. Okay, here you essentially have two plots that I'm just going to redo by myself. Okay, which is that what happened, just to recap, I have two particles into the game. I have a bath particle, okay, which follow the equilibrium curve. And this bath particle actually is going to freeze out at some point, okay? And so, I mean, essentially doesn't follow this exponential suppression up until the end of the days. And I'm also assuming that my bath particle is going to decay at some point, okay, to the dark matter. And while it was around and very present and still relativistic up until the end, my bath particle through decay was producing my dark matter, okay? Once the amount of my bath particle gets Boltzmann suppressed, so sorry, with the red color, I'm representing YB, okay? With the blue color, I'm representing Y chi, okay? Once my bath particle number density becomes Boltzmann suppressed, my production through freezing comes to a halt, and essentially this is a log plot, okay? So let's say that the extra decay, final decays of my bath particle doesn't change. And I have, at the end of the day, Y chi infinity, my number density of dark matter that builds up to freezing time and just stay constant until today, okay? So this is the case of freezing. Now, just to maybe I can even go back to this expression here, which was essentially what was driving my relic abundance, okay? I have seen that even with the exact formula, I have Y chi that is proportional to the decay rate of my bath particle. The decay rate of my bath particle goes as lambda chi, okay? Lambda chi to the power 2, okay? Bath particle, dark matter particle, and leptons, okay? In the case of my leptophilic scenario. And this explains why in the case of freezing, okay, in the case of freezing, I have essentially this dependency omega h squares proportional to lambda chi. So this explains why this curve rises with increasing value of the coupling at small value of the coupling. Now let me rapidly go through the superwind mechanism, which is just slightly different, okay? Here, what I'm going to assume, and yeah, sorry, I have to hurry up a little bit. So, I mean, if you have an urgent question, go ahead, but I would like to have a chance to go through the two other mechanisms. So if I can continue, I just jump to the superwind mechanism. So as you have seen, I mean, within the framework of the leptophilic dark matter, if I go to even lower couplings than what is usually assumed for a freezing dependence, I mean, freezing production of dark matter, I end up with very, very small decay rate. So lambda chi is very, very small. Is even smaller than the lambda chi that we needed for freezing. Okay, so I'm really looking to very small coupling. So it means the decay rate B2 chi is very small. Okay, meaning that actually the lifetime, essentially, you can also see it, is very long. Okay. So what could very well happen in this story is that essentially I could imagine a case where I have my bath particle that was in chemical and kinetic equilibrium with the bath, then goes through chemical decoupling, has frozen out, and after some long time, okay, so this is, let's say, X chemical decoupling of my bath particle. After some long time, okay, it's going to decay fully to the dark matter, okay? And so essentially my dark matter density, I expect it to boom, get fixed at that time. So, I mean, the difference between superwind mechanism and freezing is that you are going to essentially produce, I mean, your decay rate is so small that actually you only end up producing your dark matter at very late time after freeze out, okay? Notice that in general, okay, even if the production of dark matter through freezing is essentially negligible, again, I'm assuming I have a log plot here, but I mean, you should also think that actually there might already have been some dark matter production through freezing, but because we are essentially in a log plot here, I mean, essentially in this setup, it's essentially super WIMP production. So make production of dark matter by the bath particle after it has frozen out. That is the relevant process here, okay? Now, in this setup, in order to guess what is the relic abundance of dark matter, it's relatively simple. If I have just simply the total set of bath particles that after some time just simply decay to the dark matter, okay, I essentially can expect that the co-moving number density of my bath particle at the time of freeze out can only go to one place. I mean, it's essentially going to, for every bath particle I have, I'm going to get a dark matter particle, okay? So, I mean, I can directly guess that the amount of dark matter I'm going to have at the end of the day is directly related to the amount of bath particle I had at freeze out. So essentially, if I go to relic abundance of dark matter, I essentially expect, I mean, relic abundance of dark matter is m chi times y chi at infinity. So essentially, it's the relic abundance of the bath particle, which is mb times yb, okay, divided by the mass of the bath particle times the mass of the dark matter particle. So in the essentially super WIMP mechanism, you see that apart from the fact that you have the mass of the dark matter that enter into the game, you have essentially nothing about the coupling of dark matter to the path of the particle that enters into the game, apart from the fact that you have assumed that this coupling is sufficiently small in order for super WIMP to happen well after chemical decoupling of your bath particle. So this is essentially rule of thumb or like common sense, let's say, but you can get exactly this result. So again, I didn't, say, but in red I had the bath particle density, and in blue I have my dark matter density. Again, you can go back to your equations, your Boltzmann equation for your dark matter and your bath particle, and if your bath particle, let's assume that your bath particle that was in chemical equilibrium and kinetic equilibrium in the early universe, that has chemically decoupled from the plasma at some time, but as all particles interacting weakly, we can expect that kinetic decoupling happens sometimes after, okay? I can still use the usual ansatz that we are using from the beginning of this lecture, that the distribution of my bath particle divided by the distribution of my bath particle at equilibrium should have a direct relation with the number density of my bath particle divided by the number density of my bath particle at equilibrium. So essentially, looking at the evolution of this bath particle at time after the freeze out of my bath particle, the only process that can still affect the relic abundance of the bath particle, it's its decay around that time after freeze out. So I'm looking at these times. The only thing that is going to affect the number density of my bath particle is the decay. So essentially, the evolution equation for my bath particle is going to be directly influenced by the decay of this bath particle. Okay. Keeping in mind that my bath particle, okay, the initial condition is that at time of freeze out, my bath particle had its freeze out number density. Okay, I solved this and I end up just simply with the fact that my bath particle should just simply be the freeze out bath density times an exponential decay. I mean, I just have a constant and boom, suddenly at super wind time, let's say, I will call it like that, I have an exponential decay, and I can just from this expression, okay, let's say that x super wind square is essentially this quantity R gamma divided by 2 to the power minus 1, where R gamma is the same quantity we already saw before, which is the decay rate of the bath particle into the dark matter, which is a very suppressed rate now, times essentially Planck mass divided by the mass of the bath particle square. You plug this dependency into the evolution equation now of the dark matter distribution function that you integrate out and that you look at dark matter number density evolution, okay? And at the end of the day, you plug these quantities, you integrate, okay, from super WIM until today, from the beginning until super WIM time, and essentially you just recover y chi infinity equal y bath at the time of freeze out. So you just plug these quantities, you take this assumption, you just recover that indeed, at the end of the day, if you have super WIM mechanism, you have to expect that your relic abundance is just going to be set by the relic abundance of the bath particle at the time of freeze out divided by the mass of the bath particle multiplied by the mass of the dark matter. So as I said, this does not depend at all essentially of this lambda coupling, apart from the fact that you have assumed that you have a very late decay after freeze out. So essentially, again, if I go back to my plot of relic abundance evolution as a function of my coupling lambda chi, okay, essentially, when lambda chi is extremely suppressed, at the end of the day, the only thing that is relevant is the bath particle relic abundance, which is set again by gauge couplings and not, it should be j to the minus 4 here. So it's just set by gauge couplings and not by lambda chi. So again, my relic abundance of dark matter for very suppressed coupling, in the case where I have a partner, okay, it gets essentially constant, okay? It's fixed by the relic abundance of the mediator. Now for the 10 minutes maybe I have left, I just want to briefly mention this intermediate situation. So we said that, okay, we go from freeze out, where we had our relic abundance that was having some dependency in the coupling, to mediator annihilation. If I have a small mass splitting, I can have mediator annihilation freeze out, where I have my dark matter that do not depend at all on the dark matter coupling. And then, I mean, there is a jump, poof, I go to freeze in, where actually I have a dependence in the coupling, increasing, and then I have to relate these two situations. I have freeze in, and then poof, I have mediator freeze out. What happened in between? Okay, and in the few minutes that I have left, I want rapidly and briefly to address what is happening in between. And this is what I'm going to refer to as conversion-driven freeze-out, or equivalently, co-scattering freeze-out. That might be the two ways you have been hearing about this situation. So I mean by going to lower and lower value of the coupling, I cannot consider mediator annihilation freeze-out until the end of the days. Okay. At some point, there is an assumption that I'm doing when I did co-annihilation that breaks down. And this assumption that breaks down is essentially that I can assume that my dark matter and its partner are in chemical equilibrium. So what breaks down is that when I looked at co-annihilation or mediator annihilation freeze-out, I have assumed that conversion processes are fast around the time of chemical decoupling of dark matter and the mediator. Okay. Here, my couplings, okay, that are driving this kind of conversions. So in the case where I have conversion-driven freeze-out, conversion processes are these processes that essentially we're setting the relic abundance for freeze-in, for example. These are also conversion processes. The mediator that decays into the dark matter. So if these conversion processes do not happen very fast enough, at some point you end up in a situation where dark matter is neither in chemical equilibrium nor in kinetic equilibrium, okay? So there is an intermediate step between being not at all and being completely in chemical equilibrium. And we are looking at this intermediate situation, essentially. So in order to address this situation, I cannot look at the Boltzmann equation, the simple Boltzmann equation for the total dark matter number density evolution, which is the simplification we have done in the case of co-annihilation. I really have to look at the evolution equation for the different particles in the dark sector, and I mean really take into account all the terms and especially the conversion terms. So these terms that I have in a box here in yellow. So we really have to solve this coupled set of equations and take into account these terms. Okay, so notice that here I'm still doing the assumption actually that I'm in kinetic equilibrium. And this is not guaranteed from mediator annihilation up until the moment where we have freezing, okay? But just to essentially say what are the first things that are coming into the game is that you should essentially not stop at your Boltzmann equation where you have the sigma V effective, okay? And where at the end of the day, for very small coupling, it looks like your relic abundance do not depend at all on the coupling, but you should definitively think that at some point, if this coupling is too small, these kind of processes are not going to be in equilibrium again anymore. And I should definitively, I mean, really follow them up to be certain of what is going on, okay? Doing that, and I have no analytical formula for this part. I just going to explain essentially with words what are the first things that we see happening in the story. So let me take the exact picture of one conversion driven freeze out case. So this would be this picture. So here you see again the number density, the co-moving number density in the first plot on the y-axis, sorry. Here, okay. I have noticed the number density of the bath particle, which is a charge scalar in my leptophilic scenario, and the number density of the dark matter. Again, this is written in terms of time. And if I want to have mediator annihilation freeze out or conversion driven freeze out, I need a small mass splitting. Okay, so here is the situation, okay, between the dark matter and its partner. If I don't have a small mass splitting, forget about co-annihilation, forget about conversion driven. Okay, you can still have freezing, you can still have superwork. Okay, but in the case of a small mass splitting, you could very well have a situation where you have mediator annihilation freeze out or conversion driven freeze out. What happening here is that as in freezing, I'm slowly going to, let's assume that initial condition, I have no dark matter initially, and then I'm first going to produce it slowly for a time, okay? But then at some point, my dark matter abundance is going to cross essentially its equilibrium density curve, which would be the same one as the mediator evolution curve. So you see that the mediator follows as usual its equilibrium density curve, puff, up until when it freezes out and would essentially be constant, except that it can decay to the dark matter and poof, disappear at some point to decay, to completely decay into dark matter. So what happened, and here it's not, I mean, enormous, but maybe I should zoom a little bit. I mean, what happened here is that essentially I'm never going to completely follow, let's say, my equilibrium evolution for the number density of dark matter. I'm always going to end up with y chi. Whoopa. This is very big. With y chi slightly larger or equal for situation where I'm near to the mediator annihilation freeze out, slightly larger or equal than what I would have from equilibrium. And this is due to the fact that conversion processes that would transform back my dark matter to the mediator, would it be co-scatterings or inverse decays, these processes are essentially of the order of the Hubble expansion rate. So I'm very near to break here chemical equilibrium between the two species, okay? And in this situation, I do not recover exactly what would happen in mediator annihilation freeze out. I have my dark matter that does not follow the equilibrium curve, but is a little bit larger than what we would expect from equilibrium, meaning that at the moment of freeze out, essentially, I end up actually with slightly larger leftover of dark matter than in the usual mediator annihilation freeze out. I recover, and the smaller is going to the coupling, the more I am going to have my dark matter that is going to be separated from its equilibrium evolution. And this is this feature that makes that at the end of the day, I cannot expect my mediator annihilation to exist forever for any value of the coupling. At some point, I'm going to recover a dependency of omega h squared in the coupling, and I'm going to have a rising curve again, okay? This is what has been dubbed as a conversion-driven freeze-out by, among other people, Matthias Garni and Jan Heisig. And I propose you to directly go to see their paper to have more details about all this stuff. And as I said, I mean, the equations I have presented you, the last ones, they are valid while you can assume that you have kinetic equilibrium. I had a question about, I mean, can I assume that I'm in kinetic equilibrium in the case of mediator annihilation freeze out? Actually, you can check, and you are in a kinetic equilibrium actually at some point. In the conversion freeze out situation, you can expect that you will go out of kinetic equilibrium. And this is where I have put dashed line here. There in that region, actually, you should go one step further and you should really go through the unintegrated Boltzmann equation and look at the very detailed evolution of the distribution function of dark matter and the bath particle number density. Let me just, as a final just word, say that very careful, because this is not taken into account into most of the absolutely fantastic tools that are on the market, like micromegas and so on. Micromegas, for example, allows you to take into account freeze-in, completely fantastically better than what I have done here, because they don't neglect spin statistic factors and so on. And on the top of this, and the fact that you could go out of kinetic equilibrium is possibly taken into account in the Axiosis for certain matters. Okay, so I'm like it's fine. I have 2 minutes maybe for last question, or maybe it's already finished. I mean, here I depend on the organizer. So do you have one last question? So I don't hear any. So I would like to thank you all for being present, for asking questions. Thank you, thank you, thank you. And now we can, I guess we can go to the tutorial of
I'm sorry, I have questions.
Yes.
Sorry.
Can I? Or not?
Actually, I have too many questions, but I just want to ask
you can take a couple of minutes to ask. Yeah, go ahead.
Okay.
What is, from the phenomenological point of view or experimental point of view, is there a difference between super WIMP and a FIMP dark matter?
So, I mean, yes, there is, because the couplings are going to be different. So the lifetimes are going to be different. So essentially, super WIMP, you are going to have very, very, very long-lived particles. Also, I mean, for Frisin, you have long-lived particles, but at least for Frisin, if you have low enough mass, like 10 keV mass or so, you can expect to see displaced signature, for example, at colliders. For super WIMP, what you are going to have is a mediator that is so long-lived that is just going to cross your detector. So you don't know if it's Frisin or super WIMP or whatever you would like to have as a scenario like this. But I mean, with super WIMP, you essentially have so long lifetime that you might spoil, for example, Big Bang nucleosynthesis, or you are going to spoil spectral distortion from the CMB and things like that. So the phenomenology is different. I mean, the observables are different.
Okay. Okay, but those scenarios cannot be tested in direct detection at all?
In direct detection scenarios? Direct detection experiment?
Direct detection, yeah.
So Frisin, you can test it, but not for the scenarios I have given you. So if you have Frisin with a light mediator, which I have not considered, my mediator is usually larger in mass, you can actually have the possibility to test Frisin dark matter with light mediators. So this was done by, I mean, maybe many people, but among others, Thomas B and Michel Tidgat and their students, they had a paper about that like 4 years ago. So this is one example of Frisin, where you can actually test them with the usual Xeno 1-ton scenario. There are other cases where you can test Frisin with other direct detection searches. And I mean, there is a lot of literature about that by Catherine Zurek, for example, and collaborators.
Okay.
But not for the scenario I have mentioned.
Okay, thanks.
Thank you very much, Laura, for these very nice lectures. I remind you that you are still, you will be able to ask directly questions to Laura during the Gather Town session. Let's now move to the tutorial session of Gather Town. So let me just stop the broadcast.